Boom. And we're back. Excellent. So now we're going to talk about asymptotic analysis and complexity, time complexity. So asymptotic analysis is a way of discussing and measuring complexity of algorithms. So complexity, what do we mean by that? Like how many lines of, no, not how many lines of code. Um, so there's two different kinds of complexity. There's time and space complexity. So both of these are measured in terms of your input size. In data structures, we're going to be storing data, and so at the size is going to be how much stuff is in our data structure. For other algorithms, it might be amount of inputs. Like if you're reading a database, it might be how many rows are there in the database, or how many thermometer readings are we getting from this sensor, or so on and so forth, right? But for our purposes, we're going to be talking about things in terms of n, and it's going to be how much stuff is in our data structure at any given time. So, or it might be how many things have been added and removed to this data structure. So, if we're talking about inserting 100 things and removing 100 things, then our n is 200 because that's 200 operations. So you kind of think of it that as how much data is being moved around essentially. Time complexity is how long does it take to do your algorithm? How long does your algorithm run for that given input size for n? How long does it take? And then space complexity is how much space in memory or hard disk, but usually we just think about memory as gigantic. How much memory will it take? How much storage will it take to solve the problem, and this is also expressed in n, right? So, for instance, I might have an algorithm that if it has 100, if it does 100 inserts, it takes 100 milliseconds, which would be ridiculously slow, but on actual 100 microseconds or something like that. And then, but it might take up 700 megabytes of memory. Just whoa, right? So these are usually a trade-off where the more time it takes, it will generally take less memory to operate on. Or if it takes up more memory, that memory is being used to speed up the operation. Uh, we're not going to see much of that trade-off in this class, but when you start talking about um, dynamic programming in 441 in the next class, you'll start to see where you can actually get speed ups in time speed ups by using more disk space. But we'll talk a little bit about that, I think, when we get to hash tables. But um, yeah, so there is a trade off in play. Excellent. So there's one way to figure out. We're going to talk mostly about time complexity. We will occasionally talk about space complexity. You'll be expected to be able to reason about both, but we are going to be more chiefly concerned with time complexity. So there's two different ways to figure out what the time complexity of an algorithm is. One way is to just run it a bunch and measure how long it takes, right? And so, like this graph that we have in the bottom left corner here, we have time being expressed in milliseconds as the y side of the graph, is the y-axis, and then the x-axis is how much input there is. And so what we're interested in is as we increase the input size, how does the time increase, the amount of time it takes? And so our actual goal is trying to fit a function to that. Is it linear? Is it like straight like a line? This graph here though looks a little parabolic. Hmm. Hmm. And so what we're interested in is capturing how how fast does the time it takes to execute grow with respect to how much data there is there. So if I put in 100 things and it takes 5 seconds, and then I put in 200 things and it takes 10 minutes, that's that's a problem, right? you Because then if you put in 400 things, what's it going to take? 6 hours, right? So you got to make sure that your what we're trying to do is pick a function that captures that growth. And so we can run these experiments and then try to draw a line through them and say, well, this function looks like it's a good characterization of it. That's nice. Why don't we always just do that? Well, one, we have to write the code and get it to run bug free. Ugh. Right? Like, if we can we get around that? If we can get around that, we'd want to get around that. Um, Also, the results that you're getting are going to be based on the particular inputs that you used. Meaning, if it's a sorting algorithm, it, I'm going to give it all, like the data all jumbled up, but there are certain jumbles that might perform better than other jumbles, and so you're kind of you're sampling with the hopes that you get enough things that it's representative, but maybe you don't. Also, the compilers do so much optimization when they translate your code into machine code, that you would have to make sure that you're using the exact same compiler as someone else if you want to do a performance comparison. And then also your hardware, right? If you're actually using wall clock time and you're using like a Pentium 2 from 1996 or whatever, or even just something on a cell phone now, you're going to get wildly different times. And it's like, well, it means we have to run the algorithm experiments every time we upgrade our hardware? Oh, what? Ah. So, fortunately, theoretical analysis is coming to our rescue, which you might not feel that way in about 10 slides, but it's actually here to help. We could just use pseudocode. All it requires is that we, as humans, mathematically brained humans, understand what the code is doing in our heads. We don't have to actually make a compiler understand it enough to make functioning code out of it. Because we're using our brains, we can consider all possible inputs. We'll just think, well, what would take longer or shorter for this particular algorithm? We're not bound to compiler design or hardware limitations, just our own hardware limitations, which, you guys are running with probably better hardware than me, much more up to date. Uh, and the result from the theoretical analysis is that we assign an upper bound. So we come up with a function we say is an upper bound, meaning that this is the worst case. It's always going to be faster than this function would predict it, right? So if you think we come up with a function, the purpose of that function is to predict the performance of the algorithm, and the function's always going to be a little bit more gloom and doom, right? Like the actual algorithm will run faster than it. But if we have something that's a little bit pessimistic, then we can start making claims like, well, it will never run even as badly as this. This is our worst case scenario. And then if you can accept the speed of the worst case scenario, then you'll be happy with the actual speed of the function. Whereas if you have a lower bound, it's not it's not as good of a guarantee. It's not as actionable as of a guarantee. If you're unfamiliar with these functions, you're going to have to familiarize yourself with them soon. So let's take a tour. We got to go faster. The fastest function here is at the top, constant time, and then the slowest function's down here at the bottom, exponential. So let's go over our cast of characters first. Constant time algorithms are those that don't care about how much input there is. Doesn't care, right? For example, if I have an array of size 1,000,000 and I want to get the 50th element, constant time. I just look in the 50th slot. Done, right? It could be it could be 1,000,000, it could be 10 million, a billion, or 200, and I can always get to the 50th slot in one array lookup, because it just takes the beginning of the array and the size of each element of the array, multiplies it by 50, and adds it to the starting position. That's all it does. It does a multiplication and an addition. Doesn't care how big the thing is. So constant time is our fastest because it doesn't care how much data there is. That's amazing, right? It'll always just do a fixed number of things. Um, then there's linear time, which means that you're going to do a fixed number of operations for each input, right? So if I have 100, say I have 100 items, if I do 3 operations to each of the 100 items, that's linear time. Even though it's 3 operations, it's a fixed number. 3 is a fixed number. So I do 3 operations to the first one, 3 to the second, 3 to the third, all the way up to the nth, right? And so this is linear, meaning if I double the size of the inputs, I would expect the time it takes to execute my algorithm to also double. And this is one of the faster ones. That doesn't even seem that impressive. Linear is kind of a baseline. If you could do something in linear, it's pretty fast. It's generally acceptable if you can do something in linear time. Generally, because sometimes you can go even faster. I'm looking at you, binary search. All right. Then there's quadratic. Quadratic is just n squared. So remember how I said if I have, let's see, I have some examples here. Don't mess with the camera. So I have like, oh, we lost the cat, so I can use this. 1 second. Window capture. Oh no, this off. So I have guitar. I have what I have many of on hand. Uh, so I have some guitar picks here, right? Let's say we have 5. And so a linear time algorithm would say I do 3 operations on this one, 3 operations on this one, 3 operations on this one, 3 and 3, right? Now, when you get to quadratic, it's going to be different. It's going to be say I do 10 operations to this one, 10 operations to this one, 10 operations, 10 operations, 10 operations. But then I add one, and now I start doing 12 operations, 12 operations, 12 operations, 12 operations, 12 operations, 12 operations. And then I add one and I do 14 operations, 14 operations, right? That number's going up every time. Whereas with a linear, I would do 5, 5, 5, 5, 5, and then add one and 5, 5, 5, 5, 5, 5, and so on and so forth, right? So the idea is that for quadratic, as the size of your inputs grows, so too does the amount of operations you do on each one. So for this, it would be if it's I'm doing n number of operations or some factor of n on each element. And so that becomes quadratic. You're doing n things n times. So that's n squared, right? N times n is n. All right. Good night, sweet Doc Tam. And the cat is gone. We will miss him. I don't know where he went. Oh no, he's back. Boo boo boo. Important educational objective. Keep everyone interested, or at least get a cat involved. Do 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 do. Boop. Dude. Cat dude. Alright, whatever. He's back. Alright, so that's quadratic. So polynomial is just kind of stacking on that, right? If for each element in the list I'm doing n squared amount of operations, then I have an n cubed time thing. And then and then exponential is when you're trying to consider basically every permutation of the input. That's when, like all possible orderings of the input, that's when you get exponential time. It's generally considered the worst performance because you could come up with something worse. You could say n squared times 2 to the n would be worse than just 2 to the n. But exponential growth is so fast, or rather, the time it takes grows so fast that it's incredibly slow. And so we basically say if something's exponential or slower of an algorithm, we're not going to use it because exponential's too slow. I mean, exponential is absurdly slow. In fact, in 441, you'll learn about how to prove that something's NP complete, which means that like at its fastest, it's got an exponential solution. So it's bad. Then it's our friend the log. Everyone loves a log. And so log grows really slowly. It grows much slower than linear time. And so generally, if you see an algorithm splitting the input in half repeatedly, then you have a logarithmic performance. And just for those of you who haven't heard my spiel about what log is, um, log is if the log of n, the log base 2 of n, is how many times you can divide n by 2 until you get 1. Think about that, right? So if I have 80, if I want to do log base 2 of 80, or log base 6 of 87, right? How do I compute that in my head? Well, I just divide 87 by 6 and I get, what is that, 18? No. Oh no, I should have picked a division I could do. Well, 60 log 6, or yeah, anyway. I would divide 86 by 6 and get something like 80, let's just do 86 by 6. 86 divided by 6 is 14. Okay. And then I divide 14 by 6 divided by 6 is 2. Then I divide that by 6 and it's 0.3, right? So I divided 87 by 6 3 times before I got to 1 or less than 1, right? So then that's the answer. So that's what log means. How many times? So the base is, if I say log base 7 of n, I'm asking how many times can I divide this thing by 7 until I hit 1. And so we're going to, when we split things in half, if we take the input size is a certain number and then we split it in half so that it's half that, and we split that in half so it's half that, we want to count how many times we do that splitting. We can answer that with log, which is how many times can you divide this thing by 2 in half until you reach 1. That's why logarithm is so useful to us. And so when we see ourselves getting twice as close to the answer every time we iterate, then we're log. Log is the inverse of exponentiation. So as slow as exponentiation is as fast as logarithmic is. So log is very, very fast. So let's look at them. The things towards the top left corner are slow because they're growing fast, right? On a size of 2, that thing takes 10 units, right? Whereas over here, at a size of 2, I'm taking like 1 unit, and then even at a size of 10, I'm only taking 2, right? This thing is 5 times faster, even in this context. It's more than 5 times faster. Right, so we have our friend the log at the bottom. I apologize if you're colorblind, but I'll trace over this. So this one's log of n. Then there's n times log of n, which we can see is a little slower. It's a little slower. And then we have n. So n's actually in the middle here. So it goes log n, n, n log n. And then we have 2 to the n is up here. Wait, whoa. I just got done saying that 2 to the n is the slowest, but it's not. It looks like n cubed is the slowest over here. Well, if we actually expand this out, the problem size, we'll see that at the problem size of 10 is when the exponential function starts growing faster, and if you grow it out to, do I have another one? Ah, darn. If you grow it out to 100, then it's like the only line you would see was the yellow one, because it's just so much slower than everything else. So that's the relative speeds that we're talking about. They're in completely different performance classes, these different functions. So our goal here is going to be to label algorithms with functions. So what we're doing is, like I said earlier, we're picking a function that provides a worst case scenario for that particular algorithm. We drop constant multipliers, so we're not super concerned with the fine details here. For instance, if we find that something takes 3 operations per element, that would be 3 times n, right? Makes sense. Well, we actually just simplify that to n. Because what we're saying is, as long as it's a fixed number, we don't care. If it's 3, if it's 10, if it's 20, I don't care, as long as when n grows, that number stays constant. So a 100n algorithm is considered the same as a 2n algorithm as far as asymptotic analysis is concerned. And you say, well, what if it's like a million? What if the constant is huge? Still, as your problem grows, if they're both n-time algorithms, their performance will resemble each other. There'll be 2 lines that are kind of like splayed off from each other, whereas a curve is always eventually going to be worse. N squared is still just going to be worse than any kind of constant n algorithm, unless you have some guarantee that your problem sizes are small. Also, lower order items are dropped. So if I have n to the 4th plus n squared, we don't care. That adds like, that's such a small amount. That would be um that would be like saying, "Oh, I'm really upset about my schedule next week." "Oh, what are you doing?" "Oh, I'm climbing Mount Everest and trimming my toenails." It's like, "What?" Why would you even mention trimming your toenails? Getting an end of the 4th algorithm to execute is a massive, massive thing. Whereas n squared is tiny by comparison, right? Whereas, clipping your toenails may seem massive compared to the act of like thinking about apples. I don't know, right? So they're just what we call orders of magnitude different tasks, right? Like climbing Mount Everest is one, then like going to the grocery store, then, maybe brushing your teeth to petting a cat, right? These are all different scales of effort. And they're kind of absurd to try to compare them as if they're on anywhere the same scale. And that's the same thing we do with algorithmic speeds. So we basically drop the smallest term when we see a plus sign, and when we see a constant being multiplied by something, we can ignore it, which is great. It really simplifies the math to like, oh, I don't care about this. Goodbye. Excellent. Um, there's 3 cases of analysis. We're going to talk mostly about worst case analysis, because that's what big O characterizes. But a worst case analysis looks at the weirdest permutations of the inputs. Like if an evil programming demon came and like was going to put together the worst possible input so your function runs as slow as it possibly can, we want to capture the speed of that, because then we know that we're going to do better than it for the rest of the time. So if we could figure out what the worst case is, then we'll be good. Uh, we will occasionally talk about the best case, which is, well, what if you get like a really easy input? How fast can it go? Because there might be a huge gap between those. And then on the last day of class, we're going to talk about average case or amortized analysis, when we try to look at the performance over a span of time. Like if I do 100 operations, what's the average speed that they take? Just if I randomly sample 100 different permutations, how fast will this go? So what are the cases for a bike ride? The best case would be like going downhill. The average case would be going on a straight plane, and then the worst case would be, biking up a sheer cliff or something, like biking up a steep incline. If we're trying to look for an element in the list of size n, well, what's our best case? We find it because it's the first thing we look at. It's the first element of the list. What's the worst case? It's not in the list, and we have to look at the whole list to determine that. And then what's the average case? It's somewhere in the middle. We find it halfway through, right? So these are the kinds of different kinds of analyses. Let's just compare two algorithms. Insertion sort is n squared and merge sort is n log n. Because you see we dropped that 1/4 and that 2. So with 1,000,000 operations per second, when we have 1,000,000 items, merge sort takes 40 seconds and insert insertion sort takes 70 hours. And that's n squared and n log n. Those are pretty close. If we look at a small number of elements here on, like down here where there's only 200, if we look at a small number of elements, it doesn't seem that bad. But it's actually a huge difference, right? If you were going to buy, if there were two Roombas on the market, one that could clean your house in 70 hours, which is just sort of 3 days, or one that could clean it in under a minute, which one would you buy, right? Right. It's like there wouldn't even be a point of comparing them. All right, here we go. We're going to talk about the would you rather at the end. This class is going to run a little long because the class exercise is kind of built in to this lecture. Big O notation describes the worst case scenario, and then big omega describes the best case. If it's actually the same for a particular algorithm, you can use big theta of that function to describe it. We're going to skip over the mathematical definition now because I want to talk to you about how to look at the code, right? And so any individual line of code is going to ding you a constant time. So just running one line of code, as long as it doesn't contain a call to a function, because as long as it doesn't contain a call to a function, then that individual line of code is only constant time. However, loops get tricky, right? Because with loops, you can do an operation to each element of an input, right? So that gets weird. So what we have to look at for loops is what is their termination condition, and every time they iterate, how much closer do they get? So if I say for I equals 0, I is less than n, I plus plus, that means that I'm going from 0 to n by hops of 1, which would be linear, right? I'm stopping at each point along the way to n. But if I said I'm starting at 1 and I'm going to double every iteration and I'm going to stop at n, that would be log n, because the speed that would be is I'm going from 1 and I'm doubling, so that would be equivalent to how many times can I divide n by 2 until I get to 1, which is log. That's what log means, right? And then also nested loops. So if I have a loop that is n time and it's inside of another loop that's n time, that means I'm doing an n time algorithm n times. So when a loop's inside of another loop, they multiply each other's speed, right? If they're after each other, if they're consecutive, that means they add together. And so when they add together, it's basically the slower one wins, in that it's the weakest link in that chain. All right, let's look at some examples. And because we're doing big O, we've got Oprah here to help us think through it and go with us on our journey. So first question, I'm going to leave a pause for you guys to put stuff in Discord for each one of these, but here's the first one, and pause, and we're back. All right, I hope you got it. It's constant time if you're watching this. But it's actually kind of a trick question because we're calling this mystery function. So what we have here is constant, except this mystery function, if it's n squared, then this whole thing is n squared, right? Because we're as slow as our slowest bit of code. So it's actually determined on the speed of this mystery function. But if you look at this and your first gut is to say, oh, that's constant time, then you are correct. What about this one? And pause and resume. Cool. I hope you guys got it. It's linear. So, oh wait, no. Is it linear? Is it? No, it's not linear. See, look, I made the mistake. I've done this for too long. This is constant time. Or no. Yeah, this is just constant time. Clever. Oh no, this is sum plus equals n. Yeah, never mind. This is linear time. Haha! So let's go through the thinking here, right? It's plus equals n, but sum doesn't actually affect how many times this loop iterates. Got gummed up in the works. All right, so if we compare, this loop that we have right here is now just inside of here with some variable names changed and the operation changed. So what's this one? Pause and resume. Okay, I hope you got it. Because this is an end time loop nestled gently inside of another end time loop, it's n squared. This one's n squared. Hmm. Hmm. Let's think about this one. Pause and resume. All right. This one also n squared. What was different? Well, we're looping by I, right? And so the way you would actually solve this is you would come up with the summation that this loop represents, which would be the sum of all integers between 1 and j, and you would get n times n plus 1 over 2, which is n squared. But you would have to come up with a summation for all this stuff. The intuitive thing here is that for half of it, this I is going to be pretty close to n, and so you're going to be doing n squared for most of the execution of this, is the more intuitive version. But to actually math this out, you would have to come up with a summation that represents these two for loops like in aggregate. But I will just tell you, when you see something like this, it's still n squared. Next one. Okay, whoa, there's more code now. This is getting I don't know about it either. Yeah. So this is the last exercise that we just did, and then we have another chunk of code down here. So what do you guys think it is? Pause and then resume. Excellent. All right. Oh, by the way, for those of you watching later, still n squared, because it's n squared plus n, because they're consecutive, and because n squared is a higher order thing, it's much slower, we just remove it, right? And you can see that why we'd remove this. If we wanted to optimize some code here, we'd want to optimize the n squared part, not the n part. The n part is not the one killing our performance, it's the n squared part. All right, how about this one? Pause it and resume it. Excellent. So hopefully you saw this times 2, which means that we're getting twice as close to our destination each time. Which means that the outer loop is log n and the inner loop is n. So this is n log n. Uh-oh. Wait. And that's it. We're done. So what we're gonna do now is go into the little Discord channels for your teams. You can summon me for some live coding or discuss the solution. I generally won't just give you the solution without, kind of helping you guys through it, but I'm happy to do that if you summon me. If you don't, I will not come in unless you summon me. Maybe I will. Who knows? I'm crazy. I'm wild. I'm unpredictable. So enjoy that and have a good day. Bye.